octet rule I keep referring to. The octet rule, it just shows that molecules or ions tend to form compounds, or we could say structures, in which the atoms are surrounded by 8 electrons each. Here's the crazy part. We have some exceptions. So to begin with, we have some issues with hydrogen. We've already said that hydrogen is too small. We've also said, we haven't said yet, but we're going to say beryllium is also very, very small. Boron is very, very small. And then beryllium, I know it's on the left-hand side, and it usually does ionic bonding, but it can be used for examples for covalent bonding also. It's kind of a weird little element. So hydrogen, he doesn't form 8. He only forms 2 electrons. That's all he fits around him, which is 1 bond. Kind of like imagine if you have a marble, how many beach balls can you fit around it? Not very many because the marble's too small. Beryllium can hold 4 electrons, and that is 2 total bonds. And then boron can hold 6 electrons, which is 3 total bonds. Once we get past beryllium, we're finally large enough to follow the octet rule. So all of those atoms will use 8, 8, 8, 8, 8. They all want to get to 8. So does everyone below them, but everyone below them is of a special size. And what that means is that if the molecule kind of forms that has more than 8 in the middle, they're big enough to accommodate it. So it's like they aim for 8, but everything here and down, all of these, they can hold more than 8. There's different words for this. One word is expanded octet. Sometimes this is called being hypervalent. But those atoms can. So the funny part about this is that really there's only 5 elements that absolutely always, every single time, have to have 8. Carbon, nitrogen, oxygen, fluorine, and neon. Again, the other elements are aiming for 8, but they can do more. If it looks like they do, then they will, if a molecule forms. And keep in mind about the 3 ones that cannot quite make 8 electrons. And the question might come up, why do you care about the shape of molecules? Well, here's the thing. We have things like DNA that are very, very bound by shapes. We have things in industry that are very bound by the shapes that they form. So when you want to do a reaction, if you have a molecule that has some things that are going off of the sides of it, but it has empty space on the top and the bottom, that's important to know, because that means that you could have some big molecule come in and attach there or there. If, however, instead of that situation, if you have a carbon and it's all blocked up, it's got some kind of atoms on all the sides of it, there's not room for a big molecule to come in and attach to that carbon. So the shape of the atom, it affects a lot of things. It affects what kind of bonding will take place. It'll affect long range bonding. So it's really an important topic.